In this video, I'll talk through the 2025 Higher Chemistry paper and explain how I would approach each question. Starting off in the multiple choice with question number 1. In this question, we're asked for which of these is a pure covalent bond. Pure covalent, we're talking about our non-polar, and that means they'll have the same electronegativities. Those are found on page 12. It's the right-hand column. We'll just go through it and we'll write down all the values that are needed. Looking through the options, the only one that has the same electronegativity is going to be A. Our nitrogen to bromine bond would be pure covalent bond. When we're finding our values, we want to be using the 2021 published data booklet with the most up-to-date values that we're using. If you use an older data booklet, you might have slightly different numbers. In this one, we're talking about strong reducing agents. Strong reducing agents cause reduction in other substances. They make other things gain electrons. The reducing agents are oxidized. They lose electrons. Let's go through. So, undergo reduction reactions. Well, that's not true. They cause reduction reactions are found on the right hand side of the periodic table. We'll swing back to that one. Low electronegativity values, we'll swing back to that. They tend to form ions by gaining electrons. Well, no, they're going to lose electrons. We're going to rule that one out. Data booklet can help us to figure this out. So right hand side would be things like fluorine. And fluorine has the highest electronegativity value of 4. Let's do a little bit of thinking then. If we had F, which is, now whatever it's connected to will be lower than 4, unless it's another fluorine, in which case it would be the same. But in this case here, what's going to happen is the electrons will be pulled towards the fluorine with the higher one. That means fluorine is causing the other thing to lose. It's acting as an oxidizing agent. So that is not true. If they had a low electronegativity value, so let's just use fluorine still. Let's go for something like sodium, which is 0.09. I had to check it. Just like to say, I did get that off the top of my head. I'm quite proud of myself. What's going to happen then? So if we focus from sodium's point of view, sodium is helping the fluorine to gain electrons. It's going to be oxidized, the sodium is, by causing reduction in the fluorine. And that is going to be the correct answer of C for number 2. It's keeping on top of the fact that if it's an agent, that describes what it does to other chemicals. Reducing agents cause reduction. Remember, an reduction is gain. And if it causes reduction in the other chemical, it itself has to be losing the electrons. A quick jumpy way is where we can use page 13. At the top right, that's where your reducing agents are, and the bottom left are where our oxidizing agents are. If you're watching this after you've completed the course, you would have came across oxidizing agents, hopefully, in redox reactions, where things like potassium permanganate can be used to react with different chemicals. We've also got dichromate, potassium dichromate, which is used in the oxidation of alcohols into carboxylic acids, ketones, and aldehydes. So again, if that can get stuck in your head, you can look for where that is. We can then use that to match it up with the electronegativities to answer those ones about high electronegativities and low electronegativities and things like that. Next question, we are dealing with a calculation. We want to work out how many moles of Fe2 plus are required to react with this many centimeters cubed, which is a volume, and this concentration. Let's start off with the MnO4. N equals C times V. Importantly here, we have to turn our centimeters cubed into litres. That will give 0.05. We can then look at our ratio, which is where you look at the balance in numbers between the two chemicals. We have got a 1 to 5 ratio, so we want to multiply our answer by 5 to give 0.25. Pop them in the calculator and it will spit it out for you, and that makes our correct answer B. They have to catch the ratio, very important. if we were going on to work out what the, say, concentration of the second chemical is, that also involves a volume. There are, in those types of questions where you start as concentration and volume and you end as concentration, if you don't change this into litres and you don't change this one into litres, you will get the correct answer. As soon as we stop partway through the process, you're going to have a wrong answer, which is why I am very insistent that we change all of our volumes into concentrations for these types of questions. It gives us more flexibility to work our way through. This question is also proof and back up to my, let's call it what it is, hatred of this all-in-one calculation. This works, again, I'll say it very, very well if you're working with concentrations and volumes of chemical 1 and concentrations and volumes of chemical 2. As soon as it deviates from that, this is going to cause more problems than it's worth, which is why I much prefer work out number of moles, ratio, and then get your final answer, be it mass or concentration or moles as it was in this one. Rant over, moving along. We have to make sure we get the longest chain of carbons. The carbon to carbon double bond has to be in the longest chain. So looking through it, if I start from the left hand side and go along, come up and then go along, that has got 1, 2, 3, 4, 5, 6 carbons in the longest chain. Now, is there a chance that I've made a mess of this? Let's have a look. Has to be that. 1, 2, 3, 4, 5, 6. For that. Just to explore the other option, so I'm comfortable in what I'm saying, but if we go across the way, that would only be 5. That's not as much as 6. Starting here, well, that's still a smaller chain, even though it doesn't have a double bond. Going that way only gets you, well, it wouldn't be, what have I done? If we started at the bottom, that would be 1, 2, 3, 4, 5. Still not bigger. Now, luckily for me, this is where my approach has paid off massively, because if that is 6 carbons, X is what we put for 6, and only D has got 6 carbons in the longest chain. The rest are all 5. Easy peasy. Now the wrong answers are looking at the different branches of it. So what would I do next? Would I leave it like that? Truthfully, yes I would, but if we are not feeling as reckless as me, let's go through what we've got. Now why is it hex 13? Well, we've got 1, 2, 3, 4, 5, 6 carbons in our longest chain. The carbon to carbon double bond is between the third and the fourth. We take the lowest number, hex 13. There are 2 branches off of the third and the fourth. If we wanted to number the other way, it's not actually going to change anything. That'd be 3, 4, 5, and 6. It would still be double bond between the third and the fourth, and you still have 2 branches off of the third and the fourth. If we ended up being able to get smaller numbers for them, we would do it that way. But everything's set up here fairly symmetrical. We've got 2 branches off of the third and the fourth, so 3 and 4. It's 2 of the same, which is why it's dimethyl and then hexane for that. Now here I'm going to attempt to get into the brain of the person who wrote the question to see what traps and false trails they were trying to throw us. So for butane would be if someone caught that we can start from the bottom. So that's one of the kind of ways of deception that you might have been shown, that they can put it as looking like a branch but it's actually part of it. That would be the double bond in the middle, which is why it's a 2. We've then got two carbon branches is what it looks like. So diethyl is 2 carbon branches off of the second and the third. So that makes sense, but that has missed the fact that the longer chain is 6. The next 2, we're talking about pent. This is where someone has just gone straight through the middle for that. If you number from left to right, that'd be 1, 2. So that's why the 2 ene has came in. We've got an ethyl group off of the second and a methyl group off of the third. Again, I'm not saying that's correct, but that's where that answer has came from. The third incorrect option would be sticking with the chain through here, but this person has then numbered them from left to right. So the double bond looks like it's in position 3, the methyl group looks like it's coming off position 3, and it looks like there's an ethyl group off of that. But it all comes down to exploring all the different possible longest chains to be able to catch that the longest chain is indeed 6 with 2 methyl groups coming off of it. And that is where we get to there. Next one, which one's a tertiary alcohol? That means we have got 3 carbons attached to carbon with the hydroxyl group, the OH group. 2 options. Option 1, draw them all out. You'll see the answer. I'm going to show you my quick way and then I will go and draw them out just in my own time. So if you have got carbon with a hydroxyl group, well, if it was on the end of the chain, you would end up with 2 hydrogens there. This carbon is attached to 1 other carbon. That makes that one primary. You get 2 of them. You'd put it somewhere in the middle of the chain. That could be somewhere like that. There could be as many carbons either side. That's fine. That's now 2 carbons attached to the carbon with the OH. And the only way to get tertiary is if we have a methyl group coming off of the same branch, coming off the same carbon as our OH group. So then all I'm looking for here is, well, they are not coming off the same carbon. C and D are not coming off the same carbon. So my answer would be B. Because that's the only way we can get tertiary alcohol. Let's prove it by drawing out these chemicals. Second one, there's 3, that makes it tertiary. Third one, what we've got 2, so secondary. And then third one as well is secondary. A really easy mistake to make, and I actually did it as I was colouring these in to make them hopefully stand out to you, is I just on autopilot first focused in on this carbon here, but that's not the one we care about in this question. We care about the one that's attached to the OH. So for a second I was looking at that going, wait, there's 3 carbons, but that's not the one we focus on. We focus in on the carbon attached to the OH, and that'll hopefully help you with those ones. Next up, we're going to do the structure of 3-ethyl hexanoic acid. Okay, a couple of things to check. For hexanoic acid, it needs a carboxyl group. It needs a COOH. That is C double bond OOH. Yes, 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 and yes. They're all good. Next thing we can do is we could look at the longest chains of carbon, and it has to include the carbon with the double bond OOH. So from here, can I make 6? 1, 2, 3, 4, 5, 6. Next, we've got, that's going to be carbon number 1, because that's where we started our chain from, because that's the most important part. We have got 6 carbons. We have a 2 carbon branch coming off the off the third. So that's where the 3 comes from. 3-ethyl hexanoic acid. Looks like it's just going to be A as our answer. We will check the other ones because there might be certain mistakes that we have potentially made that get flagged up when we look into here. So again, we have got 6, but this time it's coming off of not carbon 2. Nope, it's not coming off carbon 3, it's coming off carbon 2. So that would be 2-ethyl hexanoic acid. Oh, the chains are the same, aren't they? Okay, so we've got 6 carbons, so hexanoic acid, but this would be dimethyl. So 1, 2, 3, 4, 5, and 6. So this would be 3,3 dimethyl hexanoic acid. And here it's important to remember the difference between dimethyl is 2 1-carbon branches, whereas this is a singular 2-carbon branch is what we're looking for ethyl. This, like C, has 2 methyl groups, but it's just this time they're 1 carbon further along, so 4,4 dimethyl hexanoic acid. Moving on, we're talking about an ester. This is an rim. Now this question looks familiar. It's from quite a wee while ago. Oh, it's an exact match for 2012. Years and years ago. Okay, so here we're talking about, we've got the information about a hydrolysis reaction, which is where the ester would have been split up. So it breaks between the C double bond O and the O, like so. When we're putting them back together, the left-hand side in all of these is going to become our acid because we need our C double bond O OH. And we need our OH on that side. There. So I'm going to draw it out just kind of funkily just to show them out. We could have drawn them out separated. I'm just conscious of space. Slash not want to draw it out that much. H there. H goes there. And then OH goes there. And then we just need to count up our sections and see if they're going to have the same number or if they're going to have the same mass. In an exam situation, if we want to kind of cut down on how much we're going to do, one of the things we could look at is, well, the fact that this one on the left has an extra oxygen, which is 16 grams, the other side to combat that extra mass must have one more carbon. If it's the same number of carbons and the other thing has an oxygen, they will not be the same mass. So that's making me want to ignore A. B could work. B is the only one that could work. Hopefully that makes sense. So if there's an extra oxygen, to combat the oxygen, the other side would have to have an extra carbon. Now, to prove it, I wouldn't just jump straight to that one. I'm lying. I would. Please don't. Do as I say, not as I do. We've got C2, H1, 2, 3, 4, O2 versus C2, H6, O. So this would be 24 and 4 and 32. That's going to be... So the left side does equal 60, but this is only 24 and 6 and 16, so that's going to be 46. They don't match up, so I was correct to ignore that one. Let's see if I was right. We've got C2H4O2. Well, we just did that one. That's 60. And then we've got C3H6 and O. We have 36 and 6 and 16. 36 and 6, 42. I can't count. There's 8. There's 8. So there's 8 hydrogens. I almost cried there. We have got 8. So now 36 and 8 is 44. Plus the 16 takes you up to 60. So B is correct. I almost thought I'd messed that up. Let's check the other one. C3H6O2 versus C3H. Let's count properly. 8O. So the right side is 60. This is, if you look at the difference between these two, we'll get an extra carbon and 2 extra hydrogens. That takes it above 60. So 36 and 6. Add 32. And that'll be 42, 74. And then the last one, C3H6O2 is 74. C2H6O, like the ones above, is going to be 46. Not the same and not both. 60 for that. So it's testing our ability to split the ester. I was good at that. Counting the number of carbons and hydrogens. I was mostly good at that. Working at the GFMs. I was good at that. And then that will give us our answer of B for that one. And this one, it's asking us about butanal. Butanal is 4 carbons. It's an aldehyde, which means the C double bond O is at the side. We put in all our H's like so. Now, when we get taught this topic, we talk about the oxidation of alcohols into aldehydes or ketones. And then aldehydes can go into carboxylic acid. In a reduction, we're going back the way. So we're going from an aldehyde back to the alcohol. How do I do that? Well, I'm going to have to change from a double bond O to an OH. And there has to be another hydrogen added on. It's 1 mole, so we're losing 2 hydrogens. That's going to be... Nope, we're gaining 2 hydrogens going this way. So we're going to be adding 2 grams of mass. And if it was an oxidation going the other way, we would be losing that too, because we'd knock off these 2 as well. It's testing our structures of aldehydes. Next up, we're asked about a ketone. A reasonably complicated ketone. So a couple of things we can do. We can look at formulas in that here. What I'd probably want to do though is I'd want to draw it out. Now I'm trying to decide. Right, let's go through the math approach. Right, so it's hept, so it's 7. That's unquestioned. It's hept, so it's 7. 1, 2, 3, 4, 5, 6, 7. I'm trying to decide where to put the on. Now, if we put it here, that is 2 on. And if we put it there, it's 2 on as well. See, when you look at the options though, I'm seeing that they're all leaning towards the right. So I can line it up to make my job easier at the end to figure out which one's matching. I'm going to pop it over. I'm going to pop it over here. And what else have we got? So I've dealt with the 2 on. We've also got ene, double bond between carbons in position 5. So we want a number from over here. So that's 1, 2, 3, 4, 5, 6, and 7. 5 is where the carbon-to-carbon double bond starts. So it'll be between 5 and 6. So my double bond is going to go there. And then I've got a methyl group coming off of the 6th one. For that. I'm going to pop in my H's. And then to get our answer, we can start working our way through and see if there's ones we can rule out. Well, we start off with CH3. All of them have CH3. We then have C to CH3. So that would be C, then bracket CH3. That is quite nice because that will rule out a couple for us. So that's incorrect. That's incorrect. Next we have a CH. And they both have that. So we're up to there. We've then got CH2. 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 I've already ruled out B because of the bit earlier on, so that's not going to work there. So this is the problem area for that one. It's got the C double bond O in the wrong place. Whereas if we keep going, our one does have the CO, and then finally a CH3 at the end. So that does have the same shortened structural formula. So all I'm doing is taking each carbon in the chain and writing down what's attached to that. If it's a bracket, that means it's got a branch coming off it, which we do. So 9 is going to be C. The sketching out is going to help quite a lot. We could go through these and try and picture them in our head. That might get a little bit muddled up. Then when I come back to it, doing my checks at the end of the paper, I can see that how I got to that answer. Saponification is otherwise known as alkaline hydrolysis. And oh look, there's the options. So if it was hydration, that's when C double bond breaks and water added. Hydrolysis is how we split our fats and oils, and also how to break down an ester and proteins. Esterification and condensation. Well, esterification is making esters. We are breaking esters. And then condensation is making esters or proteins. So it's a more kind of generalized term for that one. Next up, we have got number 11, and we're asked about emulsifiers. So fatty acid chains, these are long hydrocarbon chains. That makes them non-polar. And that means they do not like water. They are hydrophobic. So hydrophilic would dissolve in water. So that's a correct pair of terms, but not for this question. Hydrophobic dissolves in water. They are opposites. They mean that hydrophobic means it doesn't dissolve in water. Hydrophilic means it likes water, so it wouldn't like oil. Hydrophobic means it dissolves in non-polar substances like vegetable oil. What have we got next then? Here, which of these are terpene? So it's terpenes are made from isoprene. Isoprene is a 5-carbon molecule. So whichever of them has 5, has a multiple of 5 for the carbons, will be our correct answer. B is a correct answer for that. So if you can count in 5s, you'll be fine with that one. Next one. Use the graph to calculate temperature rise in degrees Celsius required to double the rate of reaction. Now, what we want to be doing is we want to be picking two relative rates that are fairly easy to read off. Now, our scale at the bottom is every little box is 1, so it shouldn't matter too much where we pick from. So I'm going to pick off of 0.4 degrees, comes off there, and 0.8 degrees comes off somewhere like that. So that's going from 0.04 to 0.08. It's going from, I make that 56 degrees to 68 degrees. That's a jump of 12. And that would give us an answer of C. We should be able to pick other values and it would still come out as being the same. So if we grab, so just to check, I'm not going to through all the combinations, but if we go for the end one, which would be 0.12, so that would be then 0.16. Run that across and run that down. That gives us, so that's 63 and 75. Again, a difference of 12. There might be some just the way the curve is turning that doesn't quite get to 12, but it'll be closer to 12 than any of the other options. So if you're unsure, you can do anything as long as it's doubled the value. I know I don't want to do them all, it's just one more though. So here, this would be 44 it's looking like, and it was 656, so 44 to 56, again, is a jump of that, so from 0.02 to 0.04 work for that one. I'm going to stick with my original numbered ones though. That is that. Next one, we're looking for the distribution of kinetic energy when a temperature is increased. So we're going to have more kinetic energy, and that means the peak shifts to the right. So T2 should have been shift across. So T2 is shift across. T2 is shift across a little bit. T2 for C is shift across. D, the peak is actually slightly to the... Would we say that's peak's the same? For that. Now, when we look back to here, a temperature rise of around about 10 degrees and a lot of reactions will double the rate. So with B and D, whether they are slightly out to the right or not, it's not far enough for me to pick that one up as the answer. And what's the difference? I see the difference. The area under the curve represents the total number of moles of chemicals that we've got. Now, if we look at what C's done, C, if we were to mathematically calculate the area under this curve, or just look at it, it's pretty much the same size. When we are moving our curve, as well as moving it to the right, we're pushing down on it. Don't know which way it's down. It's going to be lower in height than the previous one, because that area, so this area, is getting squashed over into there. Whereas in this one, we have too much of an overlap. This space is now too big. This area is too big for that one. So if you're moving to a hotter temperature, it will shuffle to the right and it will get squeezed down for there. Answer there is going to be A. Okay, next one. We are given some values to work with. Okay, so let's do a little sketch of our reaction profile. So we have our axes like so. It's saying that the forward reaction has a lower activation energy than the second one. So if we sketch this out, that's not as bad as I thought it was going to be. So it's telling us that going from the reactants up to the top is going to be 165, and then going up here is going to be 179. Enthalpy change is the difference between the reactants and the products. So if we take them away, we get 14 of a difference. We are starting higher and we're dropping down. That's going to make it a negative enthalpy change. If you're able to picture that in your brain, you wouldn't necessarily need to sketch it out. But that's how I kind of got to those things. We know the jumps from the starting to the top forwards and backwards. Difference between them is enthalpy change, and it has to be exothermic for this reaction to work. Next up, we're asked about equilibrium, and we are told about the enthalpy change for the forward reaction. So the enthalpy change for the forward reaction is exothermic, leading in nicely from the question before. Nicely if you know it, not nicely if you don't know it. And that exothermic reactions release heat to the surroundings and they warm the surroundings. When do you need to warm the surroundings? It's favoured when temperature is low, because then that will bring that back down. So we've got low temperature. It's favoured when the temperature is low, which means it's either B or it's D, B or D, yep. For a low activation energy, what that means is it's easier for the chemicals to react. It requires less energy for the reaction to take place. So a low activation energy makes it more likely for a reaction to take place, and that's going to make D our correct answer there. Next one's a bit of Hess's law. What we're looking for is how else can we get from, and that means A is going to be, look at my arrow versus the exam arrow. They're going the same way. So it's just written as it is. And then whatever that number is would be the number we put in. It's going the opposite direction for C. So we minus C. Oh, now they're wanting to know what C is. Well, I should have read the question properly, shouldn't I have? So do a bit of rearranging. Well, we can move C over to the other side. So C plus A equals B. So C equals B minus A. Or minus A plus B. Is that an option? Wow. Okay. Lovely jubbly. Well, haven't they just made that a lot more tricky than that could have been? So what I should have done if I'd read the question properly is, let's put my actual start point and end point. Because we're asked about C, well, C starts there and then ends there. Another way of doing that is go along the top and down to the bottom. A doesn't match, so C equals minus A, and then it does match B, so it's plus B. So actually, in whoever wrote this question's defense, it only became an issue because I didn't check what the focus was supposed to be. So C is the focus. So we're starting at the N2O4, and we want to end up at the bottom, so we need to go along to the left and then down to the middle bottom, and then that way it actually lines up really nicely. So minus A plus B. So if you did it well I did it, you can get to there. Do it the way it's intended, it'll make life easy. Or this one, we're looking at how we can use 1 and 2, figure out what equation 3 was. I'm going to call this equation a target, and I've got to use some combination of these two. So my preferred approach is to look at our target and figure out which equation each of the bits are in. So that's in that one. And then that is in 2 equations. If it's in more than one equation, ignore it, it will fix itself. Whereas the CO is only in that one. Now, water is only in the first one, but it's going to be fixed because we are doing something to equation 1 to fix the methanes, the CH4s. Each equation is only used once. We're not using it more than once. I'm going to show you how it all fit together. So what that's shown to me is that the first one we need to times by 2, and the second one needs reversed. To prove that, I'm going to rewrite it, but I'm going to put 2's in front of the first equation. So we've then got 2 methanes, 4 oxygens, 2 carbon dioxides, and 4 waters. And you'll see that's how that 4 water, that's how I knew that was going to fix itself. Reversing the second one means it's going to be 2 CO2 on the left now, 2 CO on the right, and then O2 in there as well. We're looking to see, is there anything that appears on left and right hand sides to be cancelled out? Well, carbon dioxide can get cancelled. 1 oxygen can get cancelled. And that leaves us with 2 CH4s, 3 O2s, 2 COs, and 4 H2Os. and that is our target. It matches target, and that means we have done the right thing. So equation 1 multiplied by 2, and then that one's reversed. And then if there was numbers, we just shove those numbers in. So 2 times whatever the first value is, and then minus whatever the second value is. For that, the higher chemistry definition about a catalyst is it lowers activation energy. As great as speeds up a chemical reaction without being used up is, it's not going to help you much at all in higher. So it does not increase the activation energy. Decreases kinetic energy, that's the lowering temperature, so it's not that. Shifts equilibrium to the right. Well, that would make it speed up one of the equations. Catalyst does not affect the position of equilibrium. It speeds up forwards and backwards, so it's not that one. It has no effect on enthalpy change. Back to another sketch here. Activation energy would be up to the hump. So it lowers activation energy. It does not affect the enthalpy change. That's why D is correct for that one. This is now my second attempt at answering this question. I misread the second half of the information. Step 1 is a 50% yield. If we started with 100 grams representing 100%, well, after going through a process that has a 50% yield, we would be left with 50 grams left over. Now, I was a bit on autopilot and I just read that the next step, step 2, would be 40%. Then I worked out what 40% of 50 was, and that got me wrongly to 20%. It's not the question saying. The question saying is that we are left over at the end with 40% of the starting material. So we have to work out what the yield of the second step is going to be. So it's a two-step process. We are told what happens in step 1 and the final outcome. What I'm trying to work out now is what percentage of 50 is the 40 grams that we've got left over. If we have 40 grams out of 50 grams times by 100, that makes that an 80% yield. So the correct answer here should have been 80%. Because if we take 80% of the leftover from step 1, 80% of 50 is 40 grams. So instead of us being given the 2 yields of step 1, step 2, we were to work out what the yield for step 2 was for that one. So if that's one that caught you out and confused you a bit, I can definitely understand that. The wording of the question was important. We also need to remember to treat each step independently. So take 50% of the first. We deal with 50% of the original value, and then we have to think about the second step separately. For one about the number of moles of a chemical, we have to first work out our formulas for each of them. So we have aluminium and phosphate, we have aluminium and sulfate. Page 9 is going to help you with sulfates and phosphates. It's PO4 3 minus, making it 3 as a valency, and sulfate's a valency of 2. So 3 and 2. Aluminium's in group 3, so it's 3 and 3. Cancels down. So we've got AlPO4 versus, swap them around, we will have Al2SO4, but we've got 3 of them. I've put them in red because they're the negative ions, as it said in the data booklet, that it's 3 minus and 2 minus for that. Right, what are we next need to do? We need to look at ratios. So it's a 1-to-1 ratio here, and it's a 2-to-3 ratio there. We're told there's 5 moles of aluminium. Now, importantly, that's 5 moles total. So that could be, let me get my maths right, 3 and 2 would give you 5. It could be 4 and 1. We don't know for certain, but we are told there's only 1 mole of phosphate. Well, if there's 1 mole of phosphate, that means there has to be 1 mole of aluminium in this chemical, because it's 1-to-1. That leaves us with 4 moles here. The 2-to-3 ratio, if you divide 4 by 2, then multiply it by 3, that gives you 6. of that. And that's going to be our answer of 6 for that. So to go from 2 to 3, we can divide by 2 gets you to 1, times by 3 gets you to 3. Something that might help, if you prefer, is, well, we could simplify this to 1 to 1.5, then 4 to 4 times 1.5, which again gives you 6. So there's different ways of doing them. Different people prefer scaling different ways. Something for scaling that always works for me is knock it down to 1, so divide by 2, then times by 3 to get up to the top. Next one, we're asked about the electron affinity, which is the energy change when 1 mole of gaseous atoms combines with 1 mole of electrons to form 1 mole of gaseous ions. So we're adding electrons instead of removing electrons. So it's similar to ionization energy, but slightly different. Element symbol as a gas. Combines means it's on the same side. And then it goes to gaseous ions. So that would be E minus gas. So that looks like A. Because this is half a mole of molecules. Half a mole of molecules. That could be right. But they've got us splitting apart. Yeah, so it's splitting. We're losing electrons, not gaining electrons. That's the ionization energy it's looking like for that one. So A would need to be correct for that one. Next up, we've got an equilibrium. Okay, the red colour fades. So how would we get the red colour to fade? Well, the equilibrium would need to shift away from red to colourless chemical, like so. Okay, what's going to make us do that? Now, we have got hydrochloric acid. Now, hydrochloric acid is H plus Cl minus. And that would add more H plus. So adds right hand side. And to fix that problem, this gets used up by making more of the left. So it's the reactant in the backwards reaction, whichever way backwards is for use. In the backwards reaction, that means it would shift left, which makes it more red. KBr is K plus Br minus. So K plus Br minus. We're adding to the right hand side. So we're going to again shift left. I'm going to just skip. So again, this is the same as an older question, which was maybe exactly the same. Very similar. So what we add in this next one, and what's Na positive OBr. Now where's OBr? Oh, yep, it's on the right hand side. And how does that then affect equilibrium? It shifts to the left. So our answer has to be C, because the other three all make it go to the left. Now let's talk about what's happening here. Now there are a couple of ways of removing chemicals from an equilibrium. One of them is to use an alkali. And an alkali would remove the H plus. Not in this case. We are doing a precipitation. Now I'm going to hazard a guess that's going to be involving the bromide. So I've got silver nitrate. Page 9 has the solubilities. So let's look for silver nitrate. Silver nitrate is there. It's a very soluble solution. If the silver then grabs onto bromide, if silver grabs onto bromide, it is an insoluble solid. And what that will do is that will drag away the bromine out of solution. So this removes Br minus. So how does the equilibrium shift to fix that? It shifts right. So we have all our chemicals floating around, H plus, OBr, all having a lovely time. This gets dragged down to form a solid, which would be the AgBr. So the numbers of that have gone down. So then this has to then react to form more of it to fix it. There. In questions where we're not adding something to the equilibrium or taking it away, a lot of times If it's a multiple choice one, the other three will all tend to do the same thing or not affect it at all for that. So precipitation removes ions from the solution, and that then causes and that would cause this equilibrium to shift to the right in this question. We're talking about an end point of a titration. Adding drop-wise near that, it means you're not going to overshoot it, so that sounds good. You can see the colour more clearly. So a white tile helps you see the colour change. A dry conical flask affects concentration, but that's not to do with the end point. And then you're ensuring everything mixes together so that everything's reacting before we add any more of the chemical. C makes it more of a valid reaction. It stops the concentration affecting the results. The other ones would all help us get that exact drip that then stops the reaction. We're asked about a burette. We need to take from the bottom of the meniscus. So 12.98765. So I'm going to say that one's 12.5. And then we're finishing at 24.3. 4, 5, 6, 7, 8, 9, 10. Yes. So the volume added is just going to be the difference between them. 24.3, 12.5, 0.8, 11.8. So bung it in your calculator and it'll spit out the answer for that one. Now moving on to section 2. We're asked about metal ions. We're given ionization energies, and we're asked for the first ionization energy equation. We can get the example from the data book on page 12. It's the element as a gas going to element with 1 plus, and then also adding on an electron. Stick in the symbol for sodium. We have got Na as a gas goes to Na 1 plus as a gas plus an electron. This would be the same way of doing it regardless of what type of chemical we've got. Even if it was a diatomic element, it's still talking about one atom. So if it was fluorine, hydrogen, iodine, chlorine, bromine, it'd still be the same. For that one, just with our letters, here we want to calculate the energy required for this to take place. So first thing I'm seeing is that this means it's 2 ionization energies. So one to take away the first and then one to take away the second. And the way these things work is it will either be the first and the second and third, or third and fourth. If we start off with the metal by itself, that is going to have came from the fact that we're using the first ionization energy, which would be, copying what I said before, Ca goes to Ca plus an electron. It has to be consecutive ones, so it's going to have to be the second one, in which case we would start at Ca1 plus, and that goes to Ca2 plus an electron. And the proof that I'm correct is, well, if we try and combine these two equations, hopefully you see that they cancel away, and it leaves us with calcium as a gas going to Ca2 plus, and because the electrons are on the same side, they add together, they don't cancel, and that gives us what we want. If we tried that with the second or the third, second and the third, that wouldn't work, or third and fourth wouldn't work as well. So it's a way of kind of checking that we're on the right track. That means we're going to need to do the first plus second, make sure we're taking calcium, 590, 1145, pop them together, 1745 kilojoules per mole. We're asked about why the second ionization energy of sodium is much higher than that of magnesium. Let's look at the electron arrangements to explain it. It's 2, 8, 1 for Na. First ionization energy removes the outer electron. And then when we go to remove another one, we need to take it from the inner shell. Versus magnesium is 282. So that first one again, we are taking that outer electron, or one of the two outer electrons, and then the second one takes away the electron from that outer shell as well. So both the electrons are removed from the outer, less tightly held shell, but in sodium, that second one comes from an inner, more tightly held electron. Question is asking us about sodium, so I'm going to focus on that one. Second ionization energy for sodium requires removal of an inner, more tightly held electron. There's less shielding of it. You can talk about it that way as well, because there's one less shell. That's going to be less shielding, more attraction by the nucleus to make it harder to remove. We're trying to explain this, so this sounds like it's going to be shielding of protons. So Mg2 positive, I said that it was 2,8, and then Na1+ is also 2,8. So, I should maybe read the question. Okay, so same number of occupied energy levels. So the other thing that can affect it is the number of protons. Well, magnesium is number 12. Sodium is number 11. And that means that magnesium has more protons. There's more protons in the nucleus. That'll be it. If we had to then go and explain it, well, the fact that there's more protons increases the nuclear charge, nuclear pool. The electrons are held more tightly, and it's a smaller atom that we have in this one. What is meant by an ionic bond is when we have an attraction between positive and negative ions. I'm getting specific what type of attraction. It's an electrostatic attraction between positive and negative ions. If we're asked about covalent, again, with covalent, it's the attraction between the nuclei and shared electrons. And if it is metallic, it's the metal ions and delocalized electrons. Next up, we have a numbery question. We need to do some scaling going on. Okay, so we have 8 tablets for 7 days. So 8 tablets, 7 days. We have 56 tablets. Okay, and they're saying each tablet, so 1 tablet equals 0.0012 moles. So 56 tablets will be 56 times that. That gives 0.0672 moles. Now let's actually read the question. So number of whole bananas have to consume to provide the same mass of potassium provided by this. Well, they're telling us that one banana is 450 milligrams. We know the GFM, we're told the GFM of potassium. So let's turn our number of moles into mass by timesing it by the GFM. 0.0672 times 39.1. That's 2.62752 grams. A milligram is 1,000th of a gram, so there'll be more milligrams, which is why we need to times this one by 1,000. You could change that milligrams there into 0.45 grams if you'd prefer. I'm just trying to get the numbers a wee bit more friendly to use. So I'm going to times that by 1,000 to give us 2627.52 grams. So how many bananas would we need to do that? Well, if one banana was 450, we are trying to work it out for 2627.52 bananas. We can scale by, starting at 450, we can divide by 450, takes us to 1, and then we can times by the 2627.52. Whatever you do to the right, you do to the left. So 1 banana divided by 450 times 2627.52 gives us 5.8 to 4 bananas. It's asking about whole numbers, so we would need to make sure we get enough potassium, we need to round that up. So there would be 6 whole bananas. Would then give you that dose plus a little bit on top of it. So that should have been milligrams there, but it still works out. Same 6 whole bananas for that one. Next up, we're asked about our bonding in the periodic table. Okay, now there are a couple of things that we can do to get to our answers a little bit quicker. Now, with lattice, the lattice that we talk about will either be metallic or ionic. We're talking about elements. We can only get ionic in compounds, requires a large difference in electronegativity. So even without looking it up, this only has one option. We'll have to have metallic in there. With molecular, well, it's only covalent that goes with molecular. So we don't have any other options. So even without looking it up, we still have that there. We're then asked about silicon and we're asked about chlorine. Well, covalent things can be either molecular as we have there, or they could be network. And the melting points and boiling points can help with that. Now, because I've done this maybe just a couple more times than you have, I know that silicon is one of our covalent networks. We can see that from the fact that it's got a high melting point and boiling point. And are we there? Versus chlorine, which has a low melting point and boiling point, making it more likely to be covalent molecular. There are a limited number of combinations that we can have, and then melting points and boiling points can help us out. This is the annotated version of the first 20 elements we have to, that we can be asked about. So if you have some of them, or hopefully all of them memorized, we would be able to jump straight to the fact that sodium's a metal, metallic lattice, silicon is covalent network, and then you've got your covalent molecular ones. We have the diatomic ones, which would be hydrogen, iodine, nitrogen, fluorine, oxygen, chlorine, and bromine. And then phosphorus and sulfur are bigger molecules. So if the question asks about diatomic, then that would be involved there. Next one, we're talking about the covalent radii, which is half the distance between the nuclei, or simply talked about as being the size of an atom. But anyway, what's the trend? We can just look in the data booklet. Sodium through chlorine is going along a period and the values are getting smaller. The size is decreasing. If we're asked to explain that, that's because there are more protons in the nucleus. It's an increased attraction for the outer electrons and pulls them together. Next one, we're asked about why there's no covalent radii listed for argon. I'm going to deviate ever so slightly from the marking scheme because the marking scheme says it does not form covalent bonds. Under some pretty extreme conditions, it can be made to react to things. It's just not likely to, or it very rarely makes bonds. If we said it does not make any bonds, then that's what the marking scheme's saying. So I'm sticking with mine. Next one, we're talking about boiling points of noble gases and the van der Waals forces. There are 3 van der Waals forces that we need to know about. There's under dispersion forces, permanent dipole to permanent dipole interactions, and hydrogen bonding. The second 2 only happen in polar molecules, which need a difference in electronegativity. They are not found in elements, so it's only LDFs that they will have. LDFs depend on the number of electrons in the chemical, and what we can see going down a group is, as the atomic numbers increasing, the number of electrons will increase, and that will increase the strength of those London dispersion forces. I'm going to put that together. So the number of electrons increases, and that causes stronger LDFs. So stronger intermetallic forces, specifically LDFs, and that's because there's no more electrons. So 1 mark for saying that its electrons are getting increasing, the electrons are increasing, and its LDFs are the interactions we're talking about, and they are getting increased stronger. For that one, okay, this one we're talking about the bonding continuum. First thing I'll do is tell them that the bonding continuum is the range of bonding dependent on the difference in electronegativities. Here's one I prepared earlier. If it's a 0 difference, it's non-polar covalent. Low differences make it polar and ionic if it's a high difference in electronegativity. I think it'd be worth telling them what electronegativity is. Electronegativity is a measure of the attraction of an atom for bonding electrons. If they have the same electronegativity, electrons are shared equally. Non-polar bond formed. There's a slight difference in electronegativity, a polar covalent bond is formed. There's a large difference. If there's a large difference in electronegativity, an ionic compound is formed. That's when the electrons are transferred from one to another. If we have non-polar bonds, it will be a non-polar compound. It will have only weak LDFs between their molecules and have a low melting point and boiling point. It will not conduct electricity. If a chemical has polar bonds but is symmetrical, it will also form a non-polar compound. Something like carbon dioxide is a good example of that. Another one would be tetrachloromethane. I can show you what I mean using PET PHET's molecular shape simulator. If you have a tetrahedral shape where all of the atoms are the same, that will be a non-polar molecule. So even if it's chlorine to carbon, which has a difference in electronegativity, overall, the charges cancel each other out. If you added one different chemical, so if you had 3 hydrogens at the bottom and 1 chlorine, that's now polar because it's not evenly surrounded by the same thing. An example which is going to be a polar molecule would be something like water. It contains polar bonds and is also a polar molecule because you've got that shape where it's non-symmetrical shape for that one. If you have polar molecules, they will have either a permanent dipole to permanent dipole or hydrogen bonding. So let's do a wee bit on that. To have hydrogen bonding, we need hydrogen directly bonded to F, O, or N. Polar compounds without hydrogen to fluorine, oxygen, nitrogen will contain permanent dipole to permanent dipole interactions. And if you have hydrogen bonding or permanent dipole to permanent dipole interactions, they will increase the melting points and boiling points of substances. Right, next I'd probably want to talk about other properties. So solubility. Polar compounds will be soluble in polar solvents like water, and non-polar compounds will be soluble in non-polar solvents like hexane and other hydrocarbons. Stronger intermolecular forces also increase viscosity and volatility. So viscosity is a measure of the thickness of the liquid, and volatility is a measure of the ease of evaporation. If they're stuck together tightly, it's harder for things to pass through them. More viscous, it's harder to separate them off and turn them into a gas, so a lower volatility for that. As with all these questions, there are very likely other things I could have talked about. Nothing else springs to mind just now, and that should hopefully be enough to pick up all 3 marks. We need a good answer for 3, a reasonable answer for 2, a limited answer for 1, and then nothing for nothing. Next one, we want a combustion reaction. Importantly for enthalpy of combustion, it has to be 1 mole of a substance. So we're going to go through the balancing steps, but we need to watch out for the fact that I need to make sure this stays as a 1. It's going to be a little bit awkward. Let's do the H's first and see if that's okay. 8 hydrogens on the left, only 2 there, so a 4 there would fix that up nicely. We have then got to look at the carbons. We need to have 3 carbons here. Now let's look at our hydrogens and see if we can make this work. So we've got 2 in the CO, which means it will be 6 oxygens there, 1 oxygen in water, so that's 4, giving you 10. We've got 1 over there, and we've got 2 there. So we're currently sitting at 3 versus 10. What we're not allowed to do, so because I don't want to change this one here, we need to somehow get the O2 to come up with a total of 9 oxygens. How would I make that happen? Well, if we times this by, and this is where I don't like it, we're going to times it by 4.5. Because if you times that by 4.5, that gives you 9 there, plus the 1 from the alcohol, we get 10 in total. So that gives us then the 10 oxygens in total on the left and the 10 oxygens on the right, and everything is now balanced and it's stuck the way it is. So in a question where we are not restricted like this, I think it looks nicer if everything was doubled up, just so it looks a bit nicer. That then isn't an enthalpy of combustion, so that's why I just have to accept this is the way it has to be for this question. We have to have a half in there. And that's, unfortunately for me, that's it. We have to. Right, next one. Calculate the enthalpy of combustion. So that's the energy released by 1 mole of a substance. So what we're trying to get to at the end is that 1 mole will give us off X number of kilojoules per mole. Couple of things we need to think about. So number 1, do we have any moles of the chemical? No, but we can work it out. N equals M over GFM. M equals 0.498 over 60 is 0.0083 moles. Okay, so that's how much chemical we've got. Now, the question doesn't tell us an energy released, but we do have EH equals CM delta T. So EH is the energy released. We are heating up water, so the heat capacity is 4.18. It's the mass of water being heated, turned into litres, which then relates to kilograms. So it'd be 0.15. 0.15 times by the change in temperature. Take them away from each other. That is 13.9. And that makes our energy released 8.7153. To get from 0.0083 moles down to 1 mole, we can divide by 0.0083. Do the same to the 8.7153. And that would give 1 mole gives off 105.04. 04 kilojoules. It's asking us to give it in moles per litre. In an nth of combustion, it's always negative, so it would be negative 1050.04 kilojoules per mole. Name the pieces of laboratory apparatus that are essential for carrying out this experiment. How many did it want? Essential. Okay, essential is quite important then. So, right, let's see what we've got. So we're measuring temperatures. So that's going to be a thermometer or a temperature probe, but something to measure the temperature. Dealing with volumes. Now, when we're doing this, we usually use a measuring cylinder. Because could you do it without a measuring cylinder? Well, or a burette, or probably a pipette more than a burette as well. But just off their values, like 150 centimeters cubed, bit of a precise value for a pipette. So measuring cylinder, go for that. We're measuring the masses, so we need a balance to measure the mass. We're going to put the water in a metal beaker. Now I'm thinking back, I don't know what you use in your school, but empty, cleaned out tin of beans or a can would work as well. Something metallic conducts the heat better. And we'd also need, for this experiment, we're burning an alcohol, a spirit burner. And that could be the ones that are like the glass with the little kind of candle wick sticking out of it. You get other ones that are like a kind of camping stove type idea that can run off certain alcohols. Whether it could work with propanol, I don't know off the top of my head. What else? Things that are like good but not needed might be something like a heat shield, where it stops heat escaping to the surroundings. But is that essential? Maybe not. I'm taking it that we're talking about this particular experiment, because if you're burning something else, you wouldn't need a spirit burner. But to burn an alcohol, you need something that will burn it. For that, the beaker needs to be clamped into place, suspended, because you're not going to hold it with your hands because you'll burn your hands. So with that then, or some other kind of way, tripod but without the gauze on top of it, which is a kind of metally network, because well, the gauze could absorb the heat, so we'd want it open and have something to kind of catch it. Some sort of suspension method for that. I don't know how many you need. Maybe if there's 2 marks, would that be 4? So your 2 of them are like 2 of them worth 1 mark kind of idea, maybe for that. I think there you can't do it without those. So how do you know how hot it is? You wouldn't. What could you just wing the volume? Do you need to measure the volume to get the right answer and to get a suitable correct value? Yeah, you do. But could you just eyeball it and wing it? Could you use a bat? Don't know. Moving on, waffling here. Why is this? So why would your nth of combustion be lower than the value expected? Part of that is heat is lost to the surroundings. That's where that heat shield would have came in handy. Incomplete combustion, where there's not enough oxygen getting to the fuel. Or, and this is in my head because I was speaking to someone during a lesson yesterday about if you leave the lid off of the spirit burner, some of the alcohol could have evaporated. So it looks like you've burned more fuel than you did. So that's why you should open the lid of the spirit burner just before you burn it to minimise the evaporation of the fuel for that one. In this one, we've got an oxygen to hydrogen ratio for ethane 1 to diol. Let's do a wee drawing of that. 2 carbons. Diol means it's got 2 hydroxyl groups. and they're off of different carbons. So something like that. It's CH4O2. They're asking us to do oxygen to hydrogen. So it's going to be the other way around. So it'll be 2 to 4, which simplifies to a 1 to 2 ratio.
Can't count. I can't count.
That is CH6. I miscounted again. O goes there, H goes there. So it is 2 to 6, which is 1 to 3. So actually count them all properly. I'm talking to myself. Then you would pick up that it's a 1 to 3 ratio that we've got there. Oxidizing agents. There are two main oxidizing agents for alcohols. Those would be acidified potassium dichromate. Now, that's a good one because it also works to tell apart aldehydes and ketones. The other one would be hot copper oxide, but that doesn't work on aldehydes and ketones. So, kind of options for that. Compound Y can be oxidized to give product Z, which turns universal indicator red. That's going to make it an acid. Let me just write up what the... I'm just going to write the order of oxidation for alcohols. So primary alcohol would go to an aldehyde and a carboxylic acid. So that means... Okay, so the fact that we're dealing with an acid means we're on this line here. Compound Y can be oxidized to give product Z, which turns universal indicator red. So that means that product Z is our carboxylic acid. We are dealing with 4 carbons. Now there's only one answer for this part because to be primary alcohol, you have to have the OH on the end of the chain, which then means that can form an aldehyde with the C double bond or the carboxyl group on the end, which means when it comes to carboxylic acid, it has to be C double bond OH on the end. So we have got butanoic acid. And that, we'll pick up the mark there. Just rearrange these more correctly drawn at the little angle. A little bit more awkward, but that's what we'd have. Next one, we have an isomer that is a secondary alcohol. Name the product formed by that. Secondary alcohols go to a ketone. A ketone with 4 would be but and one. Now, I was just thinking in my head, would we have to put a number in? Well, if we've only got 4 carbons, to be secondary, where this carbon is attached to 2 other carbons, carbon with the OH, has to be there. If it was on this carbon here, it's the same thing, so it doesn't matter for that. So then when we turn it into a ketone by making it double bond O, that has to be in position 2. If we have a bit of a longer one, so say it was pent, well, this would be pentan 2-one. This would be pentan 3-one. So there are differences. So I don't think I'd put the number in. I'm not going to put the number in. Moving on. Suitable thing, blah, 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 blah. Glassware to allow the volume to be made up to that. So we're making a standard solution in a volumetric flask. Or it's sometimes called a standard flask. Burette was rinsed. So we're doing a titration. We're rinsing out the glassware. They're doing it with water. You're better to rinse it with the chemical you're using as well. Or if you're only going to rinse it once, rinse it with the chemical. So rinse with sodium hydroxide as well, or before filling. And that's trying to make sure that we're driving off any other contaminants that could be there. Average result should be concordant. And that's going to be close agreement of 0.2. So, which ones are in close agreement? There's only 2 that are within 0.2. So we add them together and then divide it by 2. That's just going to be halfway between. That's going to be 20.4 centimeters cubed. Couple of things to keep in mind. The first one isn't automatically ignored because it's the rough or practice. It is ignored because it's so far away from the other ones. I say so far, it's 0.3, but it's far away from them. If we had happened to have, I'm just going to tweak the numbers just now, hypothetically. So say we had 20.6 and we had 22. The two that are concordant would be the first and the last one to give 20.7 as the average. So we don't automatically ignore the first one. It just so happens that the way the numbers are given, often, if not always, it is the first one is one of the ones that we can ignore. If all four of them were all spot on and all within 0.2 of each other, we would average them all as well. So think more about is the fact that they're not concordant, they're not within 0.2 of each other. That's why they're getting ignored from that one. Here we're doing our calculation. We want number of moles of the first chemical, do the ratio, number of moles of the, then work out the answer about the second chemical. Now, it's asking us for ethanoic acid. So I'm just going to pop that over here because that's what we're going to finish with. It gives us a ratio, so unless they're out to trick us, that would mean that sodium hydroxide is our second chemical, / first chemical that we're going to deal with, and that's to ethanoic acid. So they're telling us it's a 1-to-1 ratio. So if we go over to sodium hydroxide, what are we told? So I want number of moles some way, somehow for that. So we are told concentration is 0.105 times by 19.8, which would be 0.198. Pop them together. Gives us 0.02079. Now, when we've got a ratio of 1-to-1, as we know, that will do nothing to the number. I would still have it here just to make sure that we've thought about the ratio, rather than just presuming it's 1-to-1. It is here, so that's all good. If n equals c times v, c equals n over v, we're going to sub in our number of 0.02079. We divide that by the volume of ethanoic acid. There it is, 25 or 0.025. And that gives an answer of 0.0832 to three significant figures. Best of me gave from the future, I messed up with my 19.8 conversion into litres. I had said that it was 0.198 instead of 0.0198, which meant everything was out by a factor of 10. Because I kept it in my calculator, my final answer was correct, but I messed up in the in-between stages, as you can see here. I got lucky. I still got the correct final answer. I just messed up in intermediate steps. We're asked for an ionic equation. The first thing I would do is just work out the normal formula first, I would say, of potassium ethanoate. So potassium is in group 1, so it makes one bond. That's just where you can look here. Group 1, so it's going to lose one electron, that'll be fine. Or lose one electron, keep that in mind. Ethanoate, is that in here? Yes, it is. So it's CH3COO, it's got a negative charge, and it's got a valency of 1. CH3COO is 1. Swap them over, leaves you with the normal equation as just as it stands. When it comes to the ionic equation, we then put in if it's positive or negative. The one that's easier to work with here, maybe surprisingly, would be the Q, because in the data booklet it tells us that it's 1 minus. We've only got one of them because it's a 1-to-1 ratio, because it's both have a valency of 1. So with our K, well then K would have to be K positive, because now you've got 1 plus and 1 minus, so they balance each other out. To figure out the potassium one, the reduction and oxidation part can help us with that. We can see down here that we've got potassium with a 1 positive charge. So if you've got 1 positive and the other thing is 1 negative, that will balance each other out. As an example, something different. If it was KSO4, valency of 1, valency of 2, 2 and 1, that's how we get to K2SO4. SO4 in the booklet says it's SO4 2 minus. Well then, the fact is we need 2 positive to cancel it out. Here, we've got 2 1 positives, so 2 plus and 2 minus works out. for that. And as a third one, say we had something like calcium. Well, calcium is in group 2. So if you've got valency of 2 and valency of 2, swap and cancel, leaves you with CaSO4. So still SO4 2 minus, but because calcium's in group 2, it's got a 2 positive charge. So you just need one of each of them in that case. In our one for the actual exam, we needed a 1 and a 1, so that's going to work out there. Next, we're asked to calculate a mass, given some bits of information. So we've got a concentration, and we're asked to calculate the mass. So if they just proved are they going to prove my point again? So we want to get to mass. Now, how do you get mass? Mass equals N times GFM. M equals something times 60. Do we have and moles? No, but we do have concentration and volume. So N equals CV. N equals 0.45 times by 0.2. And that gives 0.09. 0.09 times 60 gives you 5.4 grams. So to prove my point about why conversion is so important, if someone doesn't do that, they'll do 0.45 times 200, which say there'd be 90 moles. Hopefully that sounds as ridiculous to you as it does to me. If you were then to turn that into the mass, that'd be saying we're adding 5.4 kilograms of powder of acid into 200 centimeters cubed of solution. So less than a can of juice with 5.4 kilograms of stuff in it is not going to happen as well. So to be on the safe side, let's get in the habit of, if we're not already, changing them into litres. Moving on, we're talking about an instant cafe drink. And we're asked, why is this thing so sucrose going to be water soluble? So my thought process is water is polar with hydrogen bonding between their molecules. Hydrogen bonding. What do you need for hydrogen bonding? You need H to FO and N. Oh look, this has OHEs. It has H's bonded to O's. It has a lot. Now, if I had proved I could count today, I'd maybe count them. I'm not doing that. You can do that for me. We're just going to say they have lots of them. They have multiple. So it's polar because of these things, and it can form hydrogen bonds. This is an example of like dissolves like, and polar chemicals can dissolve in polar solvents like water. And there is 8. Please tell them there's 8 OH groups if we're giving it a number. And moving on, we're asked about our amino acid. So we have a protein chain that's been cut up, been hydrolyzed to give these amino acid sequences. And we're trying to write the original sequence. That means that we can chop it at different points and be able to get these fragments. So I am looking for some overlap. So the first overlap I see is glyprophe would overlap quite nicely, wouldn't it, with that bit there. So there must be 2 pros. Oh, there is 2 pros for that. So which way round could we make it work? So gly cannot be at the beginning, because in this fragment it's partway through, unless there's multiple. Nah, it can't be. Right, so did I just start putting them in? Am I missing something here? Going for it. So because it's the longer of the 3, let's just try just popping in. So there has to be somewhere. Now that could be at any of the points. So that could be shuffled over 1, shuffled over 2, shuffled 3. So if I put them in here, then the glypro is the start of that, which would then make EHE there goes next. And then how do I get try your pro? Can these be flipped round? Do they have to go in that order? I wonder. Because if you make this the tail end of that, it just feels weird changing it round and putting it that way there. Because then going through them, So that's that bit. We've then got that is that bit. And that bit is that bit, but it's up back to front. Is that like, is there another way of doing it? Am I missing something? Probably. Let's have a go. Okay, I've just done some more thinking. I may have had more of a look at this. There's not a way of getting it if you keep them all in the correct order as they're written, like in the same order as they're written for that. But it doesn't say in the question that they have to be that way. So for me, the only way I can get it to work is if I flip, like I said, I flip that first one where the TYR is at the end. Or you could do the whole thing the other way around. So start with TYR, but then Pro would need to come next, then PHE would need to come next. And that takes up to that PHE of the Gly starting one. So then that in reverse, like that then takes you to Gly, and then Pro and that go together. So I found that very awkward because they two fit like a glove. Just pop the start of the middle one onto the end of the bottom one. That works. Then this just threw me a bit for a loop. This would work as presuming we're allowed to swap them around. I'm going to move on before I mush my brain too much more and go on to the one about amino acids unable to be made by the body, so must be obtained from diet, are essential amino acids. Next we're talking about palm oil and edible oil. Well, we can't say oil because I said oil. Oils are naturally occurring esters. When palm oil is split apart, so when an ester is split apart, we're making fatty acids, and well, esters are alcohols and carboxylic acids. Specifically for oils and fats, it's fatty acids and glycerol. Propane 1,2,3 triol if you're asked about the actual formula. Next up, we're looking at the saturated fat that's obtained from the hydrolysis. To make our life easier, I would recommend squishing it all together. So take all the carbons and all the hydrogens. 32 O2, C18, H34, C18, H32, O2, and then C18, H30, O2. If you look at the connections between the carbons and the hydrogens, only the first one is times by 2. It's just double it. The rest of them are all double and then either take away 2, 4, or 6. The reason for that is the only saturated one is the one that has CnH2n, and that is palmitic acid. Now to prove it, we're not going to draw this whole thing out because that's just too far. If we go for 3 carbons, double bond, let's go 4 actually. So in this one, we've got C4H, there's 8 in total with O2. So with single bonds between the carbons, it has CnH2n. If we put in a double bond, we need to get rid of 2 of the hydrogens. So that would suggest that the oleic acid has 1 carbon-to-carbon double bond. 16 times 2 should be 36, so it's not that. And then if we were to put in a second carbon-to-carbon double bond, we are then losing another 2 hydrogens. And then for this one, there's 6 hydrogens missing, which links to 3 carbon-to-carbon double bonds that are formed. So I'm not going to draw out the whole massive thing, but if you can't quite remember how it works, draw out smaller examples and then use that to kind of help you with there. Hydrogenation, no hydrogenated fats. Hydrogenation is when a carbon-to-carbon double bond breaks and hydrogen is added. That is also known as an addition reaction. That's the general term for those. Next up, we're to give the systematic name for this, which is where we go through and count up the number of carbons in a chain. That is eth. We have got a carbonyl group. That's going to make it an aldehyde or ketone. Where is that? C double bond O. It's at the side, makes it an aldehyde. That's going to be ethanal. If it's not on its own, so if it's in the center of the chain, that would be a ketone. Comes back from the fact that a primary alcohol has the C double bond O at the end of the chain. So when it becomes an aldehyde, the C double bond O will be on the end of the chain as well. For naming it, you can use the data booklet. It does have some of the names of the aldehydes and the ketones. If it's an aldehyde, you don't need a number because it'll always be on the end. If it's a ketone larger than 4, it could either be like on the second or the third, so you might need to think about a number for those bigger ones. Here we're doing a functional group. I promise this is the first time I'm looking at this paper. It just so happens I talked about the functional group. That is a carbonyl group. You would have then your hydroxyl if it was asking you about that one. What a fluke that is. Next one was to work out the number of isoprene units. Isoprene, as I said earlier, are C5 groups. We can check that as well. Buta is 4, meth is 1, so 5. Terpene here, so that's going to be 4 units big, and it tells us here 4 units is diterpenoid. Right. Remember your 5 times table, and that will help you with that. This one, we've got a monoterpenoid one. And monoterpenoid means we get 2 isoprene units, and that makes sense because there's 10 carbons in total. This has been made from 2 isoprenes coming together, so we need to be circling a 5 carbon group of carbons. Now, we need to be able to leave another isoprene unit. So why I'm saying that is, well, let's say someone went, oh, you know what, that's 5, it's got a branch. Oops, try that again. 5 carbons, and it's got a branch. Okay, but this and this are separated. So what I'm wanting to do instead is, well, there's 1, 2, 3, 4 in the chain. Nope. There's 4 carbons in the chain. That deals with the buta part of it. We need a methyl group, which we've got here. Now, it's only asking us about the terpene part, the isoprene part. It's only asking us about the isoprene part, which means I would want to ignore any OHs for that, because isoprene, it says, is just the carbons and the hydrogens. So that should be enough. That leaves you with the other one on the other side. So actually, to avoid any problems, that would be easier to circle, wouldn't it? 4 carbons to the middle and a methyl group coming off of it. Next one, we've got a little calculation dealing with milligrams per kilogram. So let's just take our time working our way through. Now this first bit is just my kind of standard scaling, where it's 5.7 milligrams is for 1 kilogram. I was pausing there because it says per day. I don't see them saying anything about a day. I feel like maybe here they should have said per day. I'm going to just presume that. So it's 66 kg adult. How do you get from 1 to 66? She times by 66. So 5.7 times 66 gives us 376.2. Just times by 66. Times by 66. Well, what are they saying now? Oh, that's milligrams. Make sure we check our unit. So 1 cup is 125 milligrams. And we are asked about 376.2 milligrams. Set it up the same. How'd you get from the 125 to 1? Yes, divide by 125. How'd you get from 1 to 376 times by 376? 1 cup divided by 25 divided by 125 times 376.2 gives you 3.0096 cups. And in this one, we're trying to not exceed it. So 3 would be below that threshold. So 3 cups would be fine. 3 cups. Iron electron equation for the reduction reaction. First thing I would do is let's see which things go together. Now, that and that is all you need apart from electrons, because there's 2 iodines, that's fine, which would suggest or mean that these ones would go together. Couple of options. One way is let's just go through both of them. Why not? Might as well. So it's I2 minus AQ going to I2 AQ. And then the other one we've got is H2O2 AQ going to plus 2H plus goes to 2H2O. Now, both of these are in the data booklet, which is nice, but iodine one first, let's go for it. So it's I2 with 2 electrons, and then 2 I minus. So find the I2, it's on the right-hand side, so the 2 electrons will go on that side. It doesn't match what's in the data booklet. The data booklet is reductions, so that means that we have got an oxidation reaction. Now, if we had asked for the reduction, that means we are dealing with the second chemical, because in a redox, one of each. And in the data booklet, potassium hydroxide, hydrogen peroxide is down at the bottom. We can see there we need 2 electrons on the left, which matches the data booklet, which means we have got a reduction. And that means that the correct answer will be the hydrogen peroxide reaction as found in the data booklet. Just spotted I missed the AQ on that one, but I'll pop it in there. You don't need the AQs, but either have them all included or none of them included. I had a bit of a mix up there. I said there's another way. If we can remember from unit 1 in the oxidizing reducing agents, this is an oxidizing agent, which means it causes the iodide to be oxidized. It itself is reduced. So if it's one of those chemicals that you come across in other topics, or you just know, that can be used to just jump ahead and get to that one. So oxidizing agents, they themselves get reduced as well. So we could have jumped straight to there. If the chemicals are both in the data booklet, so I would have just checked. So when I see that this one doesn't match, I'm not going to write it down because it's just taking up space. Sometimes one of them is a lot easier to deal with. So if one's in the data booklet and one's not, I would start with the one in the data booklet to figure out how many electrons there are. And then that will get us the number of electrons in the other one. Right, when we combine them, we're going to put both the left-hand sides together and both the right-hand sides together. Is there a trick here? So I'm checking, first of all, are they balanced individually? Well, yeah, because there's 6 and 6, that's all good. Charges are fine, aren't they? Yeah, so 2 times 2 minus is 4 minus, 2 minus and 2 minus, 4 minus, that's fine. Bottom one, no charge, 2 minus, all good for that. Now, do a bit of checking here. What appears on left and right hand sides exactly the same? It's the electrons. So we just need to rewrite it with both of the left hand sides together. S2O3, 2 minus AQ, add on I2 in solution, S4O6, 2 minus AQ, and 2I minus AQ. Gets the answer for that. If the values didn't match up, if there was different numbers of electrons, what we'd need to do first is fix that. So let's say, for talking sake, that was a 1 electron. Well, then this would need all doubled up to match. If we had a 3 and a 2, if you times the top one by 2 and the bottom one by 3, you'd end up with the same number of electrons. So that's worth checking first of all, before moving on. Next one, we're asked about a reaction rate experiment. Thiosulfate, iodine clock, goes blue-black. Very dramatic, quite quick experiment. Changes over a short period of time. What's the purpose of the water? The water is used to dilute the iodide solution. We want to be looking at all of these have 25 centimeters cubed of liquid solution in total. That means we want to keep that going. So if the volume's dropping by 5, volume of iodide solution, that is, water is going up. That'll give you 10 to keep the same one. Why must a dry beaker be used? That feels like it was in the multiple choice one. We are trying to not affect the concentrations of the solution. Okay, use information to state what happens to the rate of reaction when the concentration of iodide ions is doubled. Does this not just feel like this is I'm getting flashbacks to the more earlier on when it was pretty much the same thing. Anyway, right, what are we going for then? Let's go for, well, I like the look of this one here. That's sitting bang on the line. That's rate's going 0.05. And then if we go up to 0.4, how... Ooh. Now, I'm trying to get it on the line. Now, it's kind of just a wee bit below it. So we're between 0.1 and 0.09. So we're in that kind of 0.095 ballpark region for that. I'm looking for one. It's cherry picking the way to go, because if we cherry pick 0.1, that comes off at, because if we pick that one, it's 0.03 on the big line here. That would be halfway between, so 0.025. So that is a doubling of it. The fact is that it just doesn't quite fit on the line. I wonder what we're looking for. So not all the points that you pick will match up lovingly and perfectly, but we are in that sort of ballpark doubling region. So I'm just going to go for it. Rate of reaction. I'm going to put roughly, because it doesn't at all the points. Roughly doubles. Let's go for that. Yeah, we're now asked to work out the reaction time when the concentration was 0.025. 0.025 is halfway between. Run it up to the line, run it across. Need to figure out what we're going up in. That's 0.07. Put zeros on to make it easier. So every box must be 0.002. So this would be 0.062. And that's the only way this can work. So we have, because we're dealing with a colour change, we're going to be dealing with reaction rate equals 1 over the time. Reaction rate equals 1 over time. Then our time equals 1 over reaction rate. So time equals 1 over 0.062. 16.13, however you round it to pick up your mark. Why is increasing the concentration causing an increase in the reaction rate? First thing it does is it increases the number of particles. You get more particles in the same area, you're going to have more collisions. And that's giving us an increased chance of successful collisions. In question 7, we're dealing with bond enthalpies. We need to be thinking about breaking and making of bonds. And let's first make a little list of any bonds that need broken. We have a C, triple bond and an O. And we also have a ClCl. And then on the other side, we've got 2 CCl and 1 carbon double bonded to an oxygen. Now, this question is a little bit different to the kind of standard question because we are told the overall change and asked to work out the value of one of the particular bonds. Setup's the same, it's just that in this thing here, we don't know what that is, so we're going to work it out. We should be able to get the other ones in the data booklet. Chlorine, carbon, oxygen. So chlorine and chlorine, carbon, double bond O, there's carbon to chlorine, that's the 3 of them there. Next, we're going to total them up. So we've got, let's just call it X for easiness. So it's X plus 243, whatever that value is. And on the other side, we've got, so 2 of them would be 676, add on the 804, 1480. And the way that this works is the delta H equals the breaking, take away the making. Okay, so we've got our X, so the value we're trying to work out, that plus 243 minus 1480. Let's try it this way then. So delta H then would equal our answer minus 1237. It's going to be our enthalpy change. Add on 1237 And that means that the enthalpy will be 9.4 kilojoules per mole. Let's just rearrange this a little touch. Okay, there might be a more elegant way of doing that. I was just trying to make sure that I was going to come out with the right values at the end of it. Rearranging it in a way that spits out our missing number. To check that what we've said is correct, we can put the numbers back in, and our difference should be minus 107.6. So the making side hasn't changed. It's still going to be minus 1480. But in the breaking side, we would have the 1129.4. So it would be the 1129.4, add on my 243 before we do that. And then when you do that, it comes out with 1 minus 107.6 for that. So got a little bit lost in the weeds there of how to get it to come together, but we can always go back and check them, put them in at the end, and make sure we came out with the right answer. Just a bit awkward because it was like a part of the breaking that we're figuring out rather than the whole entire thing. So I got a wee bit lost for a second. Here we're talking about equilibrium. So one reason is that decreasing the temperature favours the exothermic forward reaction. The second one, and this was kind of percolating in my head a little bit, was to do with the fact that we're going to 80 degrees and we're involving water. So if we're involving water, that would mean that when it gets to below 80, this is going to liquefy, and then that's going to then run that off. And if you lose some water gas from the right, equilibrium shifts to the right to replace it. For that, that's quite a stretch there. In an exam condition, to kind of pull that out, well done if people did do that. It was quite a bit of a stretch, I would say, for that. But that is the second point that they're looking for. We're asked to complete this setup for this reaction. You try and work out where we're up to. One with it says react carbon dioxide with hot carbon. Carbon dioxide is made by the reaction of dilute hydrochloric acid with solid calcium carbonate. So we want a suitable container. So we could use a test tube. I'm using a flask. It doesn't say anything else. It doesn't say what particular thing we're using for it. This middle part that we're already done for is that's a good way of passing the gases through. So in this one we've got the heated carbon, so the gas that we make can pass over the hot carbon. We then need to pass it through sodium hydroxide solution before the carbon monoxide is collected, as we've got here. This is the one where we want to have one tube going into the liquid, the sodium hydroxide, and then the other pipe coming out from above it so that we can bubble it through and then it will come off at the end. I'm going to try and do a test tube or boiling tube. And that would be, so this is what I would have came up with. We've got our acid and metal carbonate producing salt water and carbon dioxide. Carbon dioxide can pass out of the flask only into the carbon, or only into the next container. It can't escape at the top. We have a stopper, passes down into the sodium hydroxide solution in the test tube. It will bubble through. It will then exit the test tube. It can't go back up through the tube because that's submerged in the solution. Out we go down to be collected over the water in the end of the setup. A couple of things I'm just double checking here. Number one, are all the pipes connected together? Looks like it. I want to have avoided blocking off any tubes, either having that or similarly here or any of those bits as best we can. Check my join here. Ooh, tiny wee bit. And just making sure that it looks okay. Plug in any gaps we need to. And that would be my answer for that one. Next up, we're asked for percentage atom economy. We find that in the data booklet. Mass of desired product over the total mass of reactants. The reason that this works is that the total mass of reactants will have to equal the total mass of the products. That's called conservation of mass. Mass is not destroyed, it's just changing from one chemical to another. We need to check if there's any balancing numbers because you have to involve them when it comes to doing these questions. This question is not doing that, it's just that there's 5 chemicals involved. So what is our desired product? It is carbon monoxide. That is the end chemical here. So that's going to go on top. So 1 mole of that would be 28 grams over total mass of reactants. That will be 65.4 and 100.1 times that by 100. Gives 16.9% atom economy. If it was easier with the numbers, we could have just taken all 3 of them together to give the same number in the bottom. Again, I'll make it very clear that if there are multiples of them, if there's balancing numbers, they have to be included. Otherwise, the masses will not be the same on both sides. And that's that one there. This one is a percentage yield question. And in this one, so percentage yield is the actual yield over the theoretical yield. In this question, we're asked about the mass of tin required in grams to produce a mass of 100 grams of tin at this temperature. Okay, so to produce a mass of 100 grams of tin, that is our actual yield. Okay, we're asked the mass of our product. Nope, we're asked the mass of the reactant. So again, this is a new way. So we are going to have to rearrange this, but we're going to do it in a bit of a different way, I would say. So it's producing 100 grams of tin. That's the actual. We want to work out the theoretical. Let's do a bit of moving around. Both theoretical would come over to the left hand side, and that's going to equal the actual divided by the percentage yield times by 100. So our theoretical mass of tin will be 100 over 64 times 100. So our theoretical yield is 156.25 grams of tin. We're not finished because we're trying to work out the mass of tin oxide that we would require to do that. So now we get down into an NMGFM calculation, but this time we're working backwards to how much of the starting chemicals we need, whereas more typically we'd be going forward to the products. So SN tin, it is N equals M over GFM. So N equals our 156.25 over 118.7. That gives 1.3163, etc. into that. The ratio is a 1-to-1 ratio. So it's going to be the same number of moles, the 1.316333. I'm keeping it like that because then I can just continue in my calculator and I don't have to retype anything. So for the SNO2, we are asked for the mass, which equals N times GFM. So that's going to be the 1.3163 and so on and so forth, times by 150.7. And then that will give me, and that gives 198.4 grams of tin oxide required at the beginning of it. Another option would be we could work through with 100 grams and work out the mass of the chemical needed and then do the scaling. I just wanted to get that out of the way first of all as well. So because it was a percentage yield of tin and we get given a mass, an actual yield of tin, I've dealt with that bit first and then I've swung back and I've got my answer in that one. Next up, we are asked to name the reactant in excess and calculate the moles of this, and calculate the number of moles of this left unreacted. First thing to do is to turn both of these into number of moles. So we have tin oxide, so N equals M over GFM, N equals 25.2 over 150.7. So that gives us 0.167, let's go 2. And then for carbon, it would be 3 over 12, gives us 0.25. Because this is a 1-to-1 ratio, they're getting used up at the same rate. So for every one SNO2 used, there's one carbon used. It means that if we were to use all of the SNO2, I'm going to substitute in the mass, I'm going to substitute in the moles that we have. Applying the 1-to-1 ratio would mean we would need 0.1672 moles of carbon. We have more of that, so this is what we have. We're investigating what we would need. That is able to happen. On the other side, if we were going to use up all of the carbon, we would have needed 0.25 of the SNO2. We do not have that much. That's not going to work. So what that means is the one that gets fully used up in the situation that works, SNO2, is the limiting factor. And that means that carbon in excess, and we're asked to tell them by how much will it be, our starting mass, our starting moles take away the moles that are going to get used up. And that will be 0.8. That will be 0.083 moles. If it was a 2-to-1 ratio, that might have changed which one's in excess if one of them is getting used up more quickly than the other. So investigate which situation do we have enough chemicals to make happen, and then base everything off of that one. In this one, we're dealing with molar volume. I know that for two reasons. Number one, it's volumes of gas. It also tells us that 1 mole of carbon dioxide is 80 litres. We have to start with the carbon dioxide because it gives us the litres and the molar volume, and it's asking us to figure out the mass at the end of the other chemical. So a little heading of CO2. My preferred approach here is, well, 1 mole is 80 litres. We have got 26.5 litres. How do we go from 80 to 26.5? Divide by 80 and times by 26.5. If we do the same to 1, that gives us 0.33125 moles of carbon dioxide. The ratio from carbon dioxide to tin oxide is 1-to-1. That means the same number of moles of the SNO2. M equals N times GFM. M will equal our number of moles times 150.7, like the question says. And it gives us a mass of 49.9 grams as our final answer. Some people like to use our relationship, which is number of moles equals volume over molar volume. VM, MV, different people do different things. My only one problem with that is that's not in a data booklet, so that's something that you have to remember or be able to figure out on the fly. Up at the top, it tells us that 1 mole is 80 litres. So that's why my preferred one's here, because it's less things we have to remember. We just use that bit of information there. In this one, we have got a flowchart, and we're asked to separate magnesium hydroxide and calcium chloride. Now, does it tell us anything about that? It does. We are separating a solution from a solid. And in order to do that, we can filter it. So filter paper in a filter funnel. So filtration. That. Okay, chlorine is recycled back as a way of keeping costs down and increasing profits. We're asked for another way of doing that. What are we starting with? Our raw material is seawater. That is going to be cheap, especially if you are in close proximity to it. So it's a raw material if we can get it straight from nature. If it has to be processed a little bit, that would be a feedstock. So something like crude oil is a raw material, whereas something like petrol from crude oil would be a feedstock. They're also producing calcium it's also producing calcium chloride. So other products could be sold. General term for that would be a byproduct, something that is also produced in the process that we can get a bit of money for by selling. In this next question, we're asked about free radical chain reactions. So there are 3 stages to them. There's initiation, propagation, and termination. We've already got the other 2. Initiation, you have no radicals, so no dots on the left, but then it makes dots. Propagation, there's dots on both sides, there's radicals on both sides. And termination, we start with radicals and we end with nothing for that. State what is meant by this. Well, free radicals have unpaired electrons. So that is representing an unpaired electron. That's what makes them so reactive. Here we're talking about enzymes, proteins unwinding and changing shape. That is becoming denatured. Denaturation. It is denaturing. For that one, a type of consumer product that has free radical scavengers in them. One of them is cosmetics, to prevent or potentially prevent damage to skin and things like that. Another thing would be in food to keep the shelf life longer. And then plastics that could be affected by the UV light would be another option for that. So some older types of plastic go yellow in sunlight if it's left for a long period of time. We add free radical scavengers are added to prevent that from happening. That's why even now plastics stay clear for a longer period of time. Next up, we're talking about pH affecting reaction rate of enzymes. Suggested by the mass of apparatus decreased, we are producing a gas and it's going to be escaping. That's going to lower the mass. So oxygen gas escaping would be a good one for that. In this next one, we're asked to compare 2 experiments. 2 potato discs were added to this much to keep constant for that. Well, the number of discs is the same, but the size or mass of the potato discs, that affects surface area and also how much of the catalase was in it. Tell you it's catalase? It does tell you. Size or mass of discs. That'd be 1. Either, like, one of them counts for that. They tell us the volume, but they don't tell us the concentration. And that would be concentration of hydrogen peroxide. Another thing that affects enzyme activity would be temperature. And it would affect both of them, so I'm just going to go for solutions. For that, which type of potato it'd come from? It'd be a bit odd if people had, 2 different types of potato to then take separate discs from as well. I suppose that could be an option. Anyway, it's fine here. Describe the effect the change in pH has on the rate of reaction. using the graph means we're probably going to want some numbers. So moving from pH 1 to pH 10, the reaction rate is increasing because the steepness of the curve is increasing. So as pH increases. Okay, so something that I've just missed, only caught there when I was looking at the numbers, pH 14 is there. So I can still talk it. So I just read that and thought this was just part of the, like, this is in between it. It was just going up in order. But pH 14 there has made us need a second sentence. So I'm sticking with between 1 and 10. Rate of reaction increases. But we now have to add in that above pH 10, or from 10 to 14, rate has decreased. And that's the idea of optimum. So if you've done biology, you've heard that, hopefully. So that's the best one it works at as well. So that was a wee hidden, sneaky one there. So between 1 and 10, it goes up, and then above 10, it's going to go down. For that one, which is the standard thing for catalysts, standard thing for enzymes, that it goes up to a peak and then it drops off above. Next up, we're talking about burning sensations of capsinoids in chilies. Two of them. Circle the amide link. One amide link is C double bond O. Do an N. Usually a H, but at least the N's important. Do we see that? I do. Make sure we're doing it off the correct one, which is this one. Yeah. So cap has that there. Super. If we're asked the other one, it would be here, but obviously that's not the right chemical. Describe a chemical test and expected result that could distinguish between these chemicals. What difference do we have? Well, they are both amides. They have got hydroxyl groups. However, it's the same hydroxyl group, so oxidizing it won't tell them apart. This one, though, has got a carbon-to-carbon double bond, which means it would decolorize bromine solution. So CAP would decolorize bromine solution. Next one, suggest why the burning sensation produced by these capsinoids would not affect by drinking water. This feels very much polar, linked to polarity again. Water is a polar solvent. These have got long carbon chains with only a little bit of polarity from the O's and stuff like that as well, but it's much more non-polar, long carbon chain. For that, word wise, let's go for non-polar compounds like these capsinoids. They will not dissolve in polar water. Next up, we're asked to determine the retention time in seconds of cap. Alright, so let's take the peak. Let's run it down. That's going to be 2.25 minutes. Well, 1 minute is 60 seconds. So 2.25 is just that times 60. Let's write that down actually. So RT equals 2.25 minutes. 1. Probably overkill here, but 1 minute 60. 135 seconds. Okay, next one. Wait, this one we're asked to calculate the cost and pence of this thing in one tube. Okay, so 60 gram contain this many percent of cap. So my first leaning is to, well, let's work out what 0.025% of 60 would be. So percent is out of 100, so that number over 100 times 60. Or you can use the percentage button in your calculator if you prefer that. That for me gives me 0.015 grams. This is in kilogram, like the price is for a kilogram, so let's turn that into into grams. So 1,000 grams is the 1,930.32 pounds. 0.015 grams will be divide by 1,000 times by 0.015. Do the same to 1930.32. Divide by 100 times by 0.015. I make that out to be 0.895. Now we have to do it into pence. So actually, I'm probably better rounding that right now to 2 decimal places. That would be to £8. £1 is 100 pennies. Times that by 100 gives us something. 2.8 pence. So again, you don't get 0.8s of a pence. So rounding it to 3 pence. Do they accept that? Just brought up the marking scheme there. It's talking about we want the nearest correct monetary unit. So that is equivalent to 2.8 pence, which would be 3 pence when we get it to that one there. We have to put it in pence because it says up there for that one. Correct. Here we want to complete the ion-electron equation for the oxidation. First thing is what's wrong with it. I've not got enough H's on the right. Let's add on 2H positive. We need to have an oxidation reaction. That means the electrons are going to be on the right hand side. There's no charge here. There's no charge here. If we put 2 electrons, it balances out the 2 positives from the hydrogen ions. Anytime you're unsure of this, reductions are on page 13. The electrons are on the left. Our one has to be on the right. That can help us know where to put the electrons. In this question, we're asked about indigestion tablets and how we can determine the mass of one of the ingredients of that indigestion tablet. One of the things that we could do is we could decompose the chemical, so we can heat it up, and then the gas that is given off, we could then collect the gas produced in a gas syringe. Based off of the equation, that would be a mixture of water and carbon dioxide. If we can cool down the water before it can get into the gas syringe, we could make sure that we're only picking up the carbon dioxide. If we manage to only collect the carbon dioxide, the volume of the gas that we can produce, we can convert that into a number of moles, thinking about the molar volume of that, thinking of the molar volume at that specific temperature, and then we can relate it because we have a 1:2 ratio from carbon dioxide to sodium hydrogen carbonate. So we can then work out, once we have our moles of carbon dioxide, we can double it to get our moles of the sodium hydrogen carbonate. Another option that says here, it reacts with acids. So we can react it with an excess of an acid. We can then either collect the gas in a gas syringe like the first one and use molar volume, or we could work out the mass of gas that's lost, which we would equate that to the carbon dioxide. This way is going to be more straightforward because it's only gas that's produced, and then that's going to be that's going to escape out any mass loss because by the carbon dioxide. We can then work out the moles of carbon dioxide that's lost. It's then a 1:1 ratio of the hydrogen carbonate, and then we can then work out the number of moles. We can then work out the mass of sodium hydrogen carbonate using its GFM, would be an option. Another thing that I was thinking is it says it's soluble, so we could make a sodium hydrogen carbonate solution. We would take our tablet, we dissolve it in deionized or distilled water, transfer it to a volumetric flask and make up to mark. We can then titrate it using our acid solution, and then using NCV, volumes and concentrations, we can work out a number of moles of the acid that was required, and then link it back through to the hydrogen carbonate through our balanced equations. So some sort of titration equipment would be helpful. With these questions, we get 3 marks for a good answer, 2 marks for a reasonable, and 1 mark for a limited answer. I've not got anything else that springs to mind of what we could talk about. That's how I would set up that question, and hopefully that'd be enough to pick up all 3 of the marks. Last question, we're talking here about skeletal formula. which has been dropped down for this question from Advanced Higher Chemistry. They are showing us how it works, that every carbon is the end of a connection. We've got double bonds with zigzag lines, and you can also be shown if there's oxygen and things present, and if there's only hydrogens coming off of a carbon, they're omitted, they're ignored, and we are going to be asked to name this chemical. First thing so one option to do it is we could just sketch it out, whole entire chemical. We would have carbon, carbon, carbon. So that's 1, 2, 3, 4, 5, 6, 7, and 8. That's going to be an octa. Like so. We've then got a carbon coming off of the second. And we have a carbon coming off of the 7th. So carbon, carbon with the branch, carbon, 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 carbon with the branch, and then sticking out like that. Now all the rest of the bits will just be hydrogens. So we've got 8 carbons in a row, single bonds between carbons, that's going to be octane. We've got 2 branches off of the 2nd and the 7th. That's 2, 7, methyl octane is what we'd have for that one. Now this one we're actually asked to draw out the whole entire chemical. So we have a carbon on the end, left hand side starting from, we have carbon with 3 H's. We've then got a carbon to carbon double bond. This carbon needs 1 hydrogen. Next one's going to need 1 hydrogen as well to make sure they're all making 4 bonds. That then takes us to this point here where we've got a carbon with a branch. There's full structure, so I'm going to put in all my hydrogens. Then we've got 2 more carbons. Hydrogen goes there. And then finish it off with the rest of the hydrogens. And just to double check, so there's 1, 2, 3, 4, 5, 6 carbons in a row. Tick. Double bond between the second and the third. Tick. And then off that's 1, 2, 3, 4th carbon, we have a methyl group. That looks good to me. So that would be 4-methyl X2-ene. If we had to name it, we don't. That's all good. Pentanoic acid, draw the skeletal formula. Now, we first have a wee sketch out of the whole entire thing. There's 5 carbons with a double bond OOH carboxyl group on the end. So that's 2 carbons up to the 3rd, then to the 4th, and up to the 5th. We've got a double bond oxygen coming off of there. And then we have our hydroxyl group OH coming off of there like that. That would be our skeletal formula. That brings us to the end of the question and the end of the paper. Thanks for watching. Goodbye.